Now to continue the program, let's get away from Ohm's law for just a moment and look at the voltmeter. This meter we are using is referred to as a DMM. That's short for digital multimeter. The DMM is a highly accurate piece of test equipment and is capable of measuring AC volts, DC volts, AC amps, DC amps, and resistance in ohms. No test bench should be without one. There are certain precautions, however, which should be observed each time you use a digital multimeter. First, make certain the meter is set on the proper unit of measurement: AC volt, DC volt, AC amp, DC amp, or resistance. Second, make sure the meter is connected properly in the circuit for the test being performed. To measure the voltage drop across a component, the meter should be placed in parallel with the device under test. To make current measurements, the meter must be placed in series with the component so the current flows through the meter and the component under test. When measuring resistance, make sure no voltage is being applied to the device being tested. If the value to be measured is unknown, then set the digital multimeter so it is on the highest scale for the unit being measured. Then work your way down to the most accurate reading. After you have completed the test or measurements, it is a good idea to set the digital multimeter to its highest AC volt setting. Resistors use color bands to indicate the value of the resistor. The first band represents the first digit of the value of the resistor. The second band represents the second digit of the resistor's value. The third band represents the multiplier, or number of zeros, following the first two digits. The fourth band is used to represent the tolerance of the resistor. The tolerance is the accuracy of the resistor. By using the resistor color code, you can read the value of any coded resistor on a printed circuit board. If there is a fourth color band, it will be gold or silver. As you notice, the colors from 0 to 9 are black, brown, red, orange, yellow, green, blue, violet, gray, and white. I'll give you a moment to review this color code. Resistor values are often measured in thousands and even millions of ohms. For this reason, a kind of shorthand is used to simplify these large values of resistance. The capital letter K, which is short for kiloohm, is used to represent thousands of ohms. The capital letter M, which is short for megohm, and is used to represent millions of ohms. Also, the Greek letter omega, which looks somewhat like a horseshoe, is used to represent ohms. Here we see four resistors. The first resistor has a color code of brown, black, brown. Since the color brown represents a 1, then the first digit is a 1. Black represents the 0, so the second digit is a 0. And since brown is again used for the third band and represents 1, that means 1 trailing 0. Therefore, this resistor with a color code brown, black, brown has a value of 100 ohms. The second resistor is color-coded brown, black, yellow. The first digit is a 1, the second digit a 0, and there will be 4 zeros following the first two digits. The value of this resistor would be 100,000 ohms, or 100 kiloohms for short. The third resistor is color-coded brown, yellow, brown. The first digit is a 1, the second digit is a 4, and there will be 1 trailing 0. That means this resistor has a value of 140 ohms. The last resistor has a color code of white, black, blue. The first digit is 9, the second digit is a 0, and there will be 6 trailing zeros. That means this resistor will have a value of 90 million ohms, or 90 megohms for short. Since all these resistors have a fourth color band of silver, they will all be accurate to within 10% of their rated values. Now remember, the capital K is for kiloohms, the capital M is for megohms. Now to begin our study of the series circuit. When the electrons flow through the negative side of the battery and go through every component in the circuit, then flow back to the positive side of the battery, it is called a series circuit. To figure total resistance for resistors in series, you simply add their values together. This series circuit contains 3 resistors. R1 has a value of 100 ohms, R2 has a value of 140 ohms, and R3 has a value of 100 ohms. Therefore, the total resistance of this circuit would be 340 ohms. This will be calculated by adding R1 plus R2 plus R3. We will assume that these are all 10% resistors. Therefore, the actual value of the total resistance could be anywhere from 306 to 374 ohms. These values were calculated by subtracting 10% from 340 ohms and by adding 10% to 340 ohms. Remember, the fourth band indicates the accuracy of the resistor. Now that we have calculated the total resistive value for this circuit, we will use a digital multimeter to verify our calculations. First, make sure the meter is set on the proper unit of measurement. Then make sure there is no voltage being applied to the circuit under test. As you notice, our DMM shows that we have a total resistance of 340 ohms in this circuit. By measuring each resistor individually, the total value of the three resistors should equal the value measured across the three resistors in series. When we measure R1, we see that R1 measures 100 ohms. When we measure the resistance of R2, our DMM shows that R2 has a value of 140 ohms. Finally, when we measure the resistive value of R3, it shows that it is 100 ohms. When we add these three values together, 100 ohms from R1, 140 ohms from R2, and 100 ohms from R3, we acquire the sum of 340 ohms, the same value when we measured all three resistors together. Now that we know the total resistance of the circuit, we will measure the voltage across the circuit and calculate for the current flow through the series resistors. Before we take the voltage reading, we must set the DMM to read DC volts. To accomplish this, we will place the meter on the DC volt scale and set it on the 20-volt range. When we connect our meter to the power source, it shows that we have 1.5 volts DC available. Now we know the resistance of the circuit is 340 ohms and the voltage being applied to the circuit is 1.5 volts. By knowing these two values, we can calculate for the current flow through the circuit. We accomplish this by using Ohm's law, formula I equals E over R. When we divide 340 ohms into 1.5 volts, we acquire a value of 0.004 amps, or 4 milliamps, which is used to indicate 4/1000th of an ampere of current. Now that we have calculated the current flow, we will verify our calculations with the digital multimeter by measuring the current flow in the circuit. When the voltage of a component was measured, we placed the meter in parallel with the component. In other words, the current flowed through the meter as well as the device under test. The current actually had two paths to flow in at the point of test. As you can see, when the meter is used to measure current, it must be placed in series with the circuit under test. This way, the current flowing through the circuit must also flow through the meter. As you noticed, the meter shows 4 milliamps of current flowing through the circuit. Even if we change the location of the test measurement, it would still show 4 milliamps of current. This is because the same current flows through every component in a series circuit. Now that we know the current flow through the circuit and we know the values of each resistor in the circuit, we can calculate for the voltage drop across each resistor in the series circuit. Once again, we will use Ohm's law to calculate the voltage drop, current times resistance. When we multiply the actual current flow of 0.00441 amps times the value of R1, which is 100 ohms, we get a voltage of 0.441 volts. Therefore, R1 will have a voltage drop of 0.441 volts. When we multiply the actual current flow of 0.00441 amps times the value of R2, or 140 ohms, we show a voltage drop of 0.618 volts across R2. And when we multiply the actual current flow of 0.00441 amps times the value of R3, 100 ohms, we get a voltage drop of 0.441 volts across R3. By adding the voltage drops of R1, R2, and R3, we get the sum of 1.5 volts, which is the voltage of the power source. Now that we have calculated the voltage drops across the three resistors, we will use the digital multimeter to verify the calculations. The digital multimeter shows the voltage drop across R1 to be 0.441 volts. The voltage drop across R2 is 0.618 volts. And the voltage drop across R3 is 0.441 volts. When we add these three values together, we acquire the sum of 1.5 volts, which is the voltage of our power source. Now that we have examined the series circuit, let's see what a parallel circuit is and what makes it different from the series circuit. In a parallel circuit, there are several paths or parallel branches through which current may flow. As the electrons leave the negative side of the battery and proceed through the circuit, some of the electrons will flow through R1, some will flow through R2, and some of the electrons will flow through R3. After the current flows through all the parallel branches, it recombines and returns to the positive side of the battery. As you can see, parallel circuits are easily identified because the current may flow through one branch or flow through another branch. If you remember that in a series circuit, the same current flowed through every component in the circuit. Since the current which leaves the power source must divide and flow through different paths, the current in any branch of the parallel circuit must be less than the total current supplied by the power source. Here we see a parallel circuit with 4 amp meters. The first meter is used to measure the entire current flow through the circuit. The 3 remaining meters read the current flow through each individual branch. If you noticed, each component in our parallel circuit is connected directly across the power source. Since the current flowing through one parallel branch does not pass through the other parallel branches, the current taken by one of the branches will be completely independent of the other branches. As long as the applied voltage does not change, the current flowing through a parallel branch will not change. Even if a branch is removed, the current flowing through each of the other branches will remain the same. The only value that will change will be the total current drawn by the circuit, as was indicated by the amp meter in series with the battery. Kirchhoff's current law states that the total current entering a parallel branch must equal the current leaving the parallel branch. In other words, if 4 milliamps of current enters a parallel branch and divides and flows through the different paths and then recombines, then the 4 milliamps of current must also leave the parallel branch. The voltage drop will be the same for all components in a parallel branch. If you recall, in the series circuit, the voltage drops changed, but the current always remained the same. Whereas in a parallel circuit, the voltages will remain the same, but the currents will change. This is because the current has more branches to flow through, and the resistance of each branch will determine the current flow through that branch. To determine the total resistance of a series circuit, we simply added the resistance values together, but in a parallel circuit, we must calculate the total resistance differently. There are 2 common formulas used to calculate for the total resistance of a parallel branch. The top formula is used to calculate circuits with 3 or more branches. The bottom formula is used when there are only 2 branches in the parallel circuit. By using either of the 2 formulas, along with Ohm's law, and by knowing Kirchhoff's current law, you can calculate the circuit characteristics of any parallel circuit. By using Ohm's law, we can calculate for the current flow through each branch of a parallel circuit. We will use the formula I equals E over R. As you recall, the voltage drop across each branch in a parallel circuit will be the same. Therefore, we know the resistance and the voltage of a branch, so our formula becomes I equals 1.5 volts divided by 100 ohms. When we divide the resistance into the voltage, the net result is a value of 0.015 amps or 15 milliamps. This is the value of current through R1. Once again, using Ohm's law, we will figure the current flow through the second branch of the parallel circuit. Our formula now becomes 1.5 volts divided by 140 ohms. This gives a value of approximately 11 milliamps. This branch actually has 10.7142 milliamps of current flowing through it. We will now calculate for the current flow through the third branch of our circuit. Once again, we divide the resistance into the voltage. The net result shows that there is 15 milliamps flowing through the third branch of the circuit. Now we know the value of current flowing through each of the branches in the parallel circuit. We can use Kirchhoff's current law to calculate for the total current flow of the circuit. When we add the 3 branches together, we get a total current flow of approximately 41 milliamps. Since we know the applied voltage and the total current flow through the circuit, we can calculate for the total resistance of the circuit. To do this, we will use Ohm's law formula R equals E over I, or resistance equals voltage divided by current. When we divide 1.5 volts by the total circuit current of 0.0407142 amps, we show that the circuit has a total resistance of 36.842182 ohms. You should note the total circuit resistance is smaller than the smallest resistor in the parallel combination. We can also figure the total circuit resistance by using one of the 2 parallel resistance formulas. When using this formula, we can only calculate for two resistors at a time. When we multiply 100 times 140, our formula becomes 14,000 divided by 240. When we divide this out, we get the equivalent resistance of 58.33333 ohms. We will now use this equivalent resistance and the value of R3 to calculate for the total resistance of this circuit. Our formula now becomes 58.333 times 100 divided by 58.333 plus 100, or 5,833.333 divided by 158.33. It shows that the total circuit resistance is 36.842182 ohms. This is the same resistance value we obtained by using Ohm's law. But we could have also used the formula the reciprocal of R1 plus the reciprocal of R2 plus the reciprocal of R3 divided into 1. Using this formula, our numbers become 1 over 100 plus 1 over 140 plus 1 over 100 divided into 1. This then converts into 1 over 0.02714. When calculated out, it also gives us a value of 36.842182 ohms. Now that we have calculated the circuit resistance and the current flow through each branch of the parallel circuit, we will verify our figures with the digital multimeter. When we measure the total resistance of the circuit, we find that it has a resistive value of 36.8 ohms. In other words, the power source will see a load of 36.8 ohms. When we place the digital multimeter in series with the parallel branches, it shows there is a total current flow of 40.7 milliamps leaving the power source. When the digital multimeter is placed in series with the first branch of the circuit, it shows there is a current flow of 15 milliamps. When the digital multimeter is placed in series with the second parallel branch of the circuit, it shows that we have 10.7 milliamps of current flowing through this branch. And finally, when we place the digital multimeter in series with the third branch, it shows there is 15 milliamps of current flowing through this branch. Kirchhoff's current law stated that the sum of the currents in all the parallel branches must equal the current which flowed into those branches. When we add the currents flowing through R1, R2, and R3 together, we acquire the sum of 40.7142 milliamps, which is the exact amount of current which flowed into the parallel branches.